So today's question is, a chain of length L and mass m lies on the surface of a smooth sphere of radius r, and it is given that r is greater than L, the length of the chain, with one end tied to the top of the sphere. Find the gravitational potential energy of the chain with the reference level at the center of the sphere. That is, this is the first part of the question. Second part is, suppose the chain is released and it slides down the sphere. Find the kinetic energy of the chain when it has slid through an angle theta. And the third part is, find the tangential acceleration dv by dt of the chain when the chain starts sliding down, the moment the chain starts sliding down. So let's take up all the parts one by one. We have to work through the mathematics of each part separately. So we can consider all the three parts independent of each other. Let's work through them one by one. So the first part first. Finding out the gravitational potential energy of the chain with the reference level at the center of the sphere. Let's call the center of the sphere as O. With respect to the point O, that means considering the potential energy at the point O to be 0, we are supposed to find out the potential energy of this chain. See that the different parts of the chain are at different heights with respect to the point O, right? And since this is a continuous chain, we need to use the method of integration to find out the potential energy of every small portion of the chain and then integrate, add up all the small potential energies and get the final answer. So to do that, let us consider a small portion of the chain over here somewhere. Let's say there's this small portion of such that it subtends an angle phi with the vertical, and its thickness of the small portion itself is d phi. Then can we say that the length of this portion, if we look at this length over here, can we say this will be nothing but r d theta, r d phi actually, we are considering the angle to be phi. So r d phi will be the small length dl of this chain, r d phi, corresponding to which the mass of this small portion dm, can we say it will be the total mass of the chain divided by its total length multiplied by the length whose mass we are looking forward to find out, dl, right? So can we say this becomes m by l into r d phi. This gives us the mass of this small portion of the chain. Now, do we understand that in order to find out the potential energy of this small portion of the chain over here, this shaded portion in green, we need to get its height also from the level of the point O. So we would be looking for this particular height over here. See that this height will be nothing but h is equal to, if we just drop a perpendicular over here, it will be nothing but r cos phi. Do you see that this length is the same, r cos phi? So that's the height of this portion of the chain, right? So we have got the height of this portion and we have got its mass. Now what will be the potential energy of this small portion of the chain? Let's call that small potential energy to be du. Can we say du will be equal to dm into gh? We know that the potential energy of a mass m is given as mgh when it is kept at a height h. So since this is a very small mass dm, its potential energy will be dm into gh. Substitute the values. Dm is nothing but m by l into r d phi, whereas h is equal to r cos phi. So we can now simplify this expression. M by l and our two r's are there, so r squared, and then there is a g also, and then we are left with cos phi d phi. This is the small potential energy du of this small portion of the chain. Now all we need to do is, since potential energy is a scalar, we can say that the total potential energy of this chain will be nothing but the sum of the small potential energies of each part of the chain that we consider like this. So that capital U, the total potential energy, is nothing but integral of du, which will be the constants kept out, integral of cos phi d phi. And since we are integrating with respect to the variable phi, we need to put the limits of phi here. See carefully in the figure that the end A of the chain, the starting point of the chain, for that particular end, the angle phi will take a value of 0 degrees. That end is right at the top. And the final point, the point B of the chain, this end point, will make an angle, let's say theta, where we can find out theta in terms of the length of the chain L and the radius of the sphere r. Do we understand that since L and r both are known to us, theta will be nothing but L by R, right? This comes from the understanding of circular motion and the circumference of a circle. So, the angle subtended by a chain of length L over a circle of radius R will be nothing but L by R. So, the final limit, the upper limit of this integral will become L by R. And now all we need to do is solve this mathematically. So, mg r squared by L, integral of cos phi is nothing but sin phi, and you put the limits 0 to L by R and solve it. So, we will get mg into r squared by L into sine of L by R minus sine of 0, which is 0 itself. So, this will be the final answer for you, right. So, that is the first answer. Now, let us go to the second part of the question. In the second part, it is said that the chain is released and it slides down the sphere. We are supposed to find out the kinetic energy of the chain when it has slid through an angle theta. See carefully that since we are supposed to find out the kinetic energy, once again directly finding out the kinetic energy of the chain will be slightly difficult. Can we try and use some law over here? Can we use, let us say, the law of conservation of energy? How? Can we say that in the process of sliding down, the chain will lose its potential energy, and whatever amount of potential energy it loses, that will convert into the kinetic energy of the chain. So, in order to find out the kinetic energy, can we just find out the loss of potential energy of the chain as it slides down by an angle theta, right? And for that, what do we need to do? We already have the initial potential energy of the chain. This is the initial potential energy. Can we just find out the final potential energy of the chain when it has already slid by an angle theta? How do we find out that final potential energy? We can use the same expression that we have used to get the initial potential energy, just change the limits of integration. Initially, the chain was at the top, the left end of the chain was at the point A, so the angle theta was 0 degrees. And the final angle was L by R. Can we say when this whole chain slides by an angle of theta, the upper end of the chain will slide down by an angle theta, so this lower limit will become theta instead of 0, and the upper limit will become theta plus L by R, right? The whole chain is sliding down, so the upper end will slide down by theta, the lower end will also slide down by theta, so both of them will have their angles increased by theta. So, all we need to do here to find out the final potential energy U2, let us call it, or U at an angle theta, can we say it will be nothing but the same integral that we have obtained there, m r squared g by L, integral of cos phi d phi. It's just that the limits of integration will be from theta to theta plus L by R for the whole chain to have slid through an angle theta. And now, when we solve this, we will get m r squared g by L sin theta or sin phi over here, and the limits of integration from theta to theta plus L by R. So, this will be nothing but m g r squared by L sin of theta plus L by R minus sin theta, right? This is the potential energy of the chain when it has already slid through an angle theta. So, this is the final potential energy. Now, can we say by the law of conservation of energy, by conservation of energy principle, the loss of potential energy U1 minus U2, initial energy minus final potential energy, should be equal to the change in the kinetic energy delta Ke, or we can also call it Ke2 minus Ke1. This comes from the law of conservation of energy, right? So, the initial kinetic energy of the chain is 0, and what we are looking for is the final kinetic energy. So, this value U1 minus U2 will directly give us that. Now, what is U1? U1 is nothing but mgr squared by L into sine of L by R. That is the initial potential energy, this value that we have calculated in the first part. Subtracted from that, mgl squared by R into sine of theta plus L by R minus sin theta, and now we can easily simplify this to get the final answer. So, our kinetic energy, which is nothing but the change in potential energy or the loss of potential energy, will be mgr squared by L into sine of L by R plus sine of theta minus sine theta plus L by R. When we simplify the above expression, this is what we shall get, and this will be the answer for the kinetic energy that the chain acquires by having slid through an angle theta. The third part now, the third part of the question is, find the tangential acceleration dv by dt of the chain when the chain starts sliding down, the initial tangential acceleration of the chain. For this, let us draw the figure once again over here to understand the scenario. So, this is the sphere, let us say, and it is at this point A that the upper end of the chain is, and the chain goes till a length L. Since the chain is curving down along the surface of the sphere, can we say that different parts of the chain will experience different tangential force? So, which force is creating the tangential acceleration? Do you understand? This chain wants to slide down the surface of the sphere only because of the gravity pulling it down, right? At every point of the chain, the gravitational force is pulling the chain down. But understand that everywhere the gravitational force is acting vertically downwards. It is vertically downwards everywhere, but its component along the tangential direction changes everywhere because the inclination of the sphere changes everywhere, right? So, can we say that if we once again take a small portion of this chain, which let us say has a mass dm because it has a length dl which is corresponding to this angle d phi that this portion subtends at the center, can we say that this small portion of the chain, because it experiences a gravitational pull of dm into g downward, its tangential component will be nothing but dm into g into sine phi. See that carefully. This angle here will also come out to be phi, so that the other angle will be 90 minus phi. So, this component along the tangent of the gravitational force will actually be the sine component. And the same thing will happen with all the other particles of the chain throughout. See that as we move along the length of the chain, the angle phi changes and hence the component dmg sine phi also changes. So, if we write a small tangential force dF along the tangential direction of this portion of the chain as dm into g into sine phi, can we say that we can find out the total tangential force and hence the net tangential acceleration by integrating the tangential force? Now, there might be a confusion here. When we try to add up all the tangential forces, understand that the direction of tangent itself is changing throughout the length, right? So, can we integrate that? Understand that we can. Here what we are writing is a scalar value, it is a magnitude of the force along the tangential direction. And understand that it is all these small tangential forces, when they add up, they create the net tangential force acting on the chain which pulls the chain down. So, we can actually integrate all of those even though they are acting at different angles. Okay, this is an important point to note here. So, now what we need to do just is substitute the values. dm we already know how to find out its value, it is m by L into r d phi, then into g sine phi, that is it. So, all we need to do now is to find out the total tangential force Ft. We need to integrate the small tangential forces everywhere, which will be nothing but integral of m by L r g into sine phi d phi. This is what we are getting, and the limits of integration, once again the phi value will take a 0 value at the point A and a value of L by R at the point B. So, the limits of integration will be from 0 to L by R. Integrate this by first taking the constants out, m by L into r g comes out, and the integral of sine phi d phi will be minus of cos phi from 0 to L by R. This is the limits. Now, when we put the limits m r g by L minus of cos L by R minus of minus cos 0. So, we will get a cos 0 first, cos 0 minus cos of L by R. This is what we shall get, and we see that cos 0 is 1. So, this can also be written as m r g by L into 1 minus cos L by R, which is our final answer for the tangential force. Now, how do we find out the tangential acceleration from here? Tangential acceleration is nothing but the tangential force divided by the mass. So, you just divide the mass over here. The mass will cancel out and we will be just left with Rg by L into 1 minus cos L by R, which will be the final answer for the third part.